So in the last week, there was a question about this melting point and the size dependence of nanomaterials. So, without really going into the details, so normally the melting point can be expressed or related to the bulk melting point of a material. This is a very simple equation, although the real dependence can be a little bit different. Okay, but more or less this basically captures the dependence of melting temperature on the size of material, and this equation is known as this Gibbs-Thomson equation. Okay, and it is based on basically phase transition. So when you look at the terms here, so definitely, so Tm stands for the melting point, then Tm bulk, so that is the melting point of bulk material, and then gamma SL is your uh, surface energy. So when you are melting something, so what you have is like you are transforming from a solid to a liquid state. So that means you normally have a surface, you create a new surface between your solid and your liquid. So you create new interfaces between your solid and liquid, and that gives you this additional surface energy. And then rho is of course your density. Then L is your latent heat, or this heat of latent heat of fusion, and D is your size of the particle.
So,
Yes,
this is density of bulk, or this is the density of
bulk,
complete solid?
density of the bulk
Okay.
solid material. And so you can then calculate this temperature dependence of the nanoparticle as a function of size. And so this here, this graph here shows how the variation is with respect to the particle diameter. I think this was for gold nanoparticle, I don't remember exactly, or gold, or maybe sodium. Okay, so but nevertheless it captures, so this dip, this jump, so here this on the y-axis what you see is a ratio of your melting point to the melting temperature of a bulk material. So that means this here represents your bulk material, and then as you decrease the size or the diameter of the particle, so you see a big jump. It sometimes it's called a like a depression. Okay, this is a temperature depression. And then yeah, it will like for very small particles, so you see like a huge drastic change, almost like 90% change in the temperature. So it is due to, again, like in a qualitative way, we can say the change is due to this change in cohesive energy, or in another way, the bond strength. And also it is, and why this changes is because you have more number of surface atoms. So since the surface atoms are larger compared to your uh, compared to your number of volume atoms. So therefore, the cohesive energy or the bond strength will change, and that is why there is a change in the temperature. Okay, so this is just a brief discussion what I wanted to have on melting temperature. So today we I want to start with something which is called so something we want to like how do we create these nanoparticles or nanoclusters from atoms? Okay, so we have seen like okay, so you can arrange the nanoparticle in the bulk, for example. So you can take atoms and arrange in a regular lattice. Okay, and then you get a long range order, so you get a crystalline solid, and then you pack them in different ways in simple cubic or like body centered cubic or FCC or hexagonal. So there are many different ways you can pack these atoms. Mostly, let's say you assume these are spherical in form, and then you get your bulk material. But how do you get, can we do the same in case of when we want to create a nanocluster or a nanoparticle? Like, can we arrange it in the same way like we did for the bulk material and get these structures? The answer is actually yes. So sometimes, like if you take, for example, only a few number of atoms, okay, so you get molecules, but and then you so you can create like more than one atom, so you get a molecule. But if you increase the number of atoms, so you normally call it a nanocluster. Okay, so maybe like 10 nanoparticles or 20 nanoparticle 20 atoms, so you create a nanocluster, right? And then if you go to 1,000 number of atoms, you call it a nanoparticle. And then yeah, more than 10,000 or a million of atoms, so you have your bulk material. Okay, so this is how you start from one single atom, and you pack them in a close packed structure. Okay, and then you get different kinds of this atoms, molecules, nanoclusters or nanoparticles, and then ultimately to the bulk material. So then when we say we are packing these atoms in a closed packed structure, let's say, so what is the efficient way to do it? What is the best possible way you can do it? So, so you always, what we want is like a closed packed structure, right? So if we say we have a 2D system, so this is basically the closed packing is achieved in a triangular lattice. This is like a hexagonal uh, lattice, what you see here. And typically it's like a 2D, two-dimensional material. So you pack in two-dimensional, sometimes you call it a monolayer. Okay, and this monolayer means like one layer of atoms which are packed in a triangular lattice or a hexagonal lattice, and that gives you the maximum density. Okay, so you get minimum volume and you get maximum density. So this is the most efficient. I mean, there are other ways like in two-dimensional lattice, so you can have square or rectangular uh, lattice as well. But this is the best way you can get a close pack structure in two dimension. So what about then 3D? So in 3D, you can then arrange the, so keep this two-dimensional structure and arrange atoms on top of it. So in a three-dimensional way, right? In the third dimension, you put atoms, and these packing are called basically your HCP and FCC. So you have hexagonal close pack and face centered cubic. So these are the two cubic structure and hexagonal close pack. So in terms of density or the packing fraction, so they are the same, almost 74% pack. Okay, but only difference is how the stacking is. So difference between HCP and FCC, they are both close pack structures, but the repetition is different. Repetition of the atomic planes, they are different. So you have A, B, and so on. That is your HCP. But in FCC, you have A, B, C, and this is the repetition in FCC. And that is how you can get a close packing in 3 dimension. So of course you will also have when we are talking about the lattice, so there will be some sites which are or voids in the unit cell, so which where smaller atoms or ions can fit in. Okay, so these are typically like known as tetrahedral or octahedral sites. Okay, so we have a close pack structure here. So the bottom one, the black one, what you see is a bottom layer, and then you put the B layer on top of it. Uh, and then what you have is you have some voids or some holes, let's say, which are which where smaller atoms or ions actually can fit in, and these are called like tetrahedral holes. So like if you look at this point here, so this point here, so if you, so this is now what we are looking at from the top. Okay, so the blue one is the top one, and the black one is the bottom layer. But when you stack it like these spheres on top of each other, so you can have small sites or voids or holes. So these are called tetrahedral voids. So that means if I put an atom here, so it will be bonded to four atoms. Okay, so this is a tetrahedral geometry. You have also points where you can put. So let's say we look at, yeah. So somewhere, let me see where we can do that. Uh, yeah, somewhere here, let's say. So this, if I put an ion or atom here in this point, so in a 3 dimension space, so it will be coordinated or bonded to six neighboring atoms. So that is an octahedral site or octahedral pole. So the tetrahedral one would look like, okay, it will be, okay, so this is something like a tetrahedral geometry, yeah, tetrahedral geometry you get. So this is your central atom which will be bonded to four different atoms. So you also have a octahedral geometry where you'll be, sorry, different. So this will be so this atom here will be a octahedral uh, site or a octahedral geometry. Okay. So this is basically you can have you can fit in smaller atoms or ions in these voids. Okay, in a lattice. Uh, I mean, this is important in the sense so many ionic solids or like when you take two different atoms to make a crystal, so this voids you can fill it up with smaller anions or so mostly the cations you have at the corners, and then in these voids you can fill the anions there or vice versa. Okay, so when you look at most of the cubic close packed structures, like either FCC or HCP, so what you have is always 12 nearest neighbors, right? So FCC structures are, for example, your silver, gold, aluminium, cobalt, copper, platinum. So many of these metallic uh, systems, they uh, arranged in a cubic or FCC lattice. So let's take one example, like any of these examples. You can take aluminium or gold, for example, and then let's say what is the smallest nanocluster we can have. Okay, so if we say to create one single lattice, okay, so what we need is like let's say one atom, and then we need 12 nearest neighbors, okay, and that will create a FCC lattice, and that means we can create a one nanocluster which is arranged in a cubic close packed structure, and it has 13 atoms, right? So what we have is 13 atoms, so 12 neighbors and plus one atom, which create a one single lattice, and that we can create, that will create the smallest nanocluster that can exist or is stable. Okay, so which will also satisfy this close packing condition. So you take one cell, one unit cell, and you get the smallest cluster that is possible. So this is a picture of one of the unit cells, and sometimes like the different names also given like cuboctahedron or decatessahedron. Okay, so different names are there, but this is basically a polyhedron with 14 sides, as you can see here. So you have six squares, six sides which are like square, and eight sides or eight faces which are triangular. Okay, so this is what you get, a polyhedral structure and the smallest cluster or a nanoparticle that you can get, which has 13 atoms. So then how do you create the next a bigger cluster? So that means then we have this 13, so we are then add a second cell around it, and then that means, so here each atom is basically almost like a surface atoms, right? There will be one atom in the center, okay, and then there will be 12 coordinates or coordination It will be bonded to 12 different atoms, nearest neighbors. But these nearest neighbors are not really completely uh, like the bond is not complete because they are partially there on the surface. Okay, so we can again pack a similar thing, and we take create or take each of these atoms. So these surface atoms. So we can take these surface atoms, and then again we can coordinate with 12 nearest neighbors. Okay, so if we do the that exercise, so we will create the next nanocluster. So again, doing it in a closed pack is like counting is a little bit difficult. Nevertheless, if you can do that, so what you get is how many atoms you can pack. So you can pack, so you can pack this 42 atoms around it, this smallest cluster. So that means the total number of atoms will be now 55. So if you have the smallest cluster with 13 atoms, so the next cluster will have 55 atoms, and this is, you have created it such a way that it keeps the close packing, uh, cubic close packing, that condition intact. So you have basically FCC lattice which are extending, and this is how you can keep this FCC structure intact. So 12 nearest neighbors, and you can create the next cluster, the stable cluster. So that means you keep the same geometrical shape. So you keep this same unit cell FCC, and you keep on adding more and more, and you create bigger clusters. And the sequence, what you have is here, this n can be equal to 1, so 13, 55. So if you go on doing like that, so you get 147, 309, 561, and so on. So this kind of, like, so you have only fixed number of atoms which can create this geometrical, which will keep the geometrical shape intact, this octapolyhedral shape, or keep the cubic close packing of the atoms. And this is actually is called a magic numbers. Okay, so I wrote it in a this here magic number. So these are actually called as structural magic number. So why structural? Because it keeps the structure the same, exactly the same as like uh, for the first nanocluster. So it keeps the cubic close packing. Even you can extend or go up to your bulk, which will be still a cubic close packing, which will be like a FCC lattice, and that and since, to maintain that, so you have to take only certain number of atoms. So you cannot take, let's say, 40 atoms and get a close packing. So to get a stable close packing, so you need this number of atoms. So 1, 13, 55, 147, and so on. So then how one can calculate this number of atoms in a stable cluster? So this is empirical formula which you can use to calculate how many numbers your cluster with a FCC structure will have. And similarly, you can also calculate the number of surface atoms. Okay, so this is your number of atoms, and this is your number of surface atoms. So that also you can calculate. What is n? N is your number of cells you want to add. So n equal to 1, n equal to 2, 3, and so on. So you can keep on adding that, and then you can get how many atoms you need to get a stable FCC structure. So if the close packing is HCP, this number can be different. Okay, of course, for the first uh, cluster, the smallest one, it is again 13. But the next one, when you fill it up, so the number of atoms to get a stable cluster will be different. So the magic number can be different for a different close packing. So it can be, so in the previous case, it was so 55, 147, and so on. But here we have 57, 153, and so this number of atoms can be different. So people have created these stable structures. So like most of one of the most investigated clusters is this gold 55. Aluminium 13 is not definite. I mean, I gave an example of that, but it really it's very difficult to synthesize this very small clusters and make it stabilize even. So even this gold 55 cluster is also not stable. So you have to coordinate with some polymers or some ligands. Okay, so you have to join some chemical ligands to it so that it becomes stable, or it is stabilized. Okay, uh, because they are, I mean, like, there are a lot of surface atoms. So this is a table which actually shows you, like, if you increase the number of cells, like how you can increase the number of atoms and number of, or the percentage of surface atoms. Okay, so let's say if you take two, so one cell, okay, you have one atom, so then two cells, you have 13 atoms. Okay, so you have 13 atoms, and 12 are surface, right? So almost 92% on the surface. So next is 55. So you have 42 atoms in the surface. So you can calculate using these empirical formula here. Okay. And what you see is, as you increase, here I think this number is wrong. So as you increase the cell numbers, so you are creating bigger and bigger clusters, and basically you are transitioning from a nano cluster to a nanoparticle, and virtually eventually to a bulk material. So this is for a FCC nanoparticle. Okay, so what this table shows only for FCC nanoparticle. So this table will be different for HCP, will be different for BCC, or even can be different for a cubic close packing with when we take two different atoms. Okay, so here this example is like you take a gold, for example, or aluminium, or platinum. Okay, so these are your FCC structures, and one single atom you have. But if you have uh, a BCC lattice, so this table will be different. If you take HCP, this is also different. And if you take even FCC with different atoms, okay, so um, probably some of you already know about this zinc blended structure. Okay, so zinc sulfide structure. Oh, I mean, it is basically FCC, but there is a transition or a shift of one atom. So even like similar to diamond structure. Okay, so there is a two interpenetrating FCC lattices, where one FCC is translated along the body diagonal by 1/4. Yeah, so Raunak, yeah, so he's asking, after how many number of cells we can consider the structure to exist in bulk form. Yes, this again is not, uh, let's say, cannot be fixed for, so it can be different for different particles. Okay, so aluminium will have a different, like, but typically, let's say, if you go from, uh, let's say in this case, if we say this FCC nanoparticle, so if you go from typically like 8 cells, okay, between 6 to 8 cells, you will actually will be going from a nanocluster or nanoparticle to really a bulk behavior, almost bulk behavior. But sometimes it can also happen, all the properties of the bulk may not happen exactly at the same, it's not like a sharp transition. Okay, so you have 6 cells and you go to 7 cells, and it suddenly becomes, everything becomes like bulk like. So some properties can become bulk like before that. Okay, so if you had, so bulk properties, so there can be like optical properties or the electrical properties, or let's say for example the melting point. So all these properties can, the transition can happen for at different cell numbers. Okay, so it depends on what properties you are looking at. So it is not like all properties will change exactly, like you go from 6 cell to the seven number of cells, and everything it becomes like bulk. So it's like a gradual transition happens. Okay, but typically it's like 6 to 8 cells. These are like number of cells which you can talk about, think about, like it is, uh, the transition, that is where it happens. But again, for some, so for example, if you take, so this number, this cell number will be smaller for metallic particles. Okay, so typically for metallic particles the transition happens sooner. But if you take semiconductor, this, for example, this gallium arsenide or zinc sulfide or zinc oxide, or these complex semiconductors. Okay, so there the size actually can be larger, and still it will retain the nanocluster, this effect, so it will not go to bulk uh, properties sooner. Okay, so it is pretty much a material dependent property actually. So all materials will not transition into bulk at the same, exactly the same size or same number of atoms. Okay, so even let's say magnetic properties, for example, so you can get, because magnetic properties, for example, if we talk about this single domain behavior, so these materials, so some materials will behave as a single domain below a particular dimension. We will see about that. Uh, so this single domain size is very different for different materials. Okay. So if you take iron, for example, it can be like about 12 to 15 nanometer. But if you take iron oxide, one kind of iron oxide, magnetite, Fe3O4, it goes to 40 nanometer, for example. And if you take another, uh, like a ceramic, there is ceramic strontium ferrite, for example. If you take that material, that uh, transition from a single domain to a multi-domain state happens around like 70 nanometer or 100 nanometer. Okay, so therefore there is no fixed uh, rule or that says that okay, at this particular number of atoms the property will go from a nanomaterial to a bulk material, the behavior will change. Okay, so it depends pretty much on the material, what are the atoms, uh, and what properties also you are looking at. Okay, so whether you are looking at the optical properties or electrical, the conductivity or the magnetic properties or the strength, so that everything can be different. Okay. So to get these magic numbers, structural or geometrical magic numbers. So what to achieve that, what basically what you need to do is you have to minimize the volume and maximize the density. Okay, and then also you get these structural magic numbers so that you get a minimum surface energy. So that is why you get these structural numbers, this atomic, so number of atoms which create a cluster. So basically you that kind of geometry leads to a maximum density and minimum surface energy. So here is example just of it's a theoretical example, let's say. So this aluminium 13 cluster, so in bulk aluminum is FCC, but when you take a cluster, aluminium 13 cluster, so it can exist in FCC or HCP, okay, or there is another, sorry. So the another one is this icosahedral. Okay, so this icos. So this is an icosahedral structure that is also possible. So which is the stable configuration out of these three? So people have done theoretical calculations using density functional theory, and so you can calculate or look at what is the thermodynamically which one is the stable cluster. That means which one will have the minimum energy, and people have found this icosahedral structure will have the minimum energy, and that is actually a stable configuration for these small clusters. Okay, so it remains, so there is a little bit of change in the actual structure. Okay, so this is basically a rearrangement of these atoms. Definitely there is not such a big or huge change in terms of the density or the number of nearest neighbors, all remain the same. Only it's a like a little bit of rearrangement of these atoms, and you can actually induce a transition from one structure to, so you can change it from FCC to icosahedral or HCP. So you can do it by applying pressure or something. You can do that. Okay, but these are some. So you can actually. So the point is you can calculate the stable configuration or the stable geometry or the stable structure of these nanoclusters using thermodynamical calculations uh, as well, because this is very difficult to actually synthesize or look at it experimentally. Okay, so you can imagine how difficult it is to create a cluster of 13 atoms. Okay, so experimentally, so therefore a lot of investigations are done in uh, experiments, sorry, theory. So these are some examples, like uh, different clusters which are stable. Okay, so carbon 20, so carbon 60 is quite a well known, this fullerene, and then you have these different clusters, and they can have all different shapes or different geometries. Okay, so all these geometries or shapes of the structure is determined by so these are all theoretical calculations, and they show that these are the stable configurations that you can get. Look, you have the same 20 number of atoms, but depending on what is the atom is, so the structure is different. Okay. Yeah, so we'll stop here and then we will start again with a different topic tomorrow. Okay. So, any question from this?
Sir, in that table, there was shell number and the diameter. So what is the connection between them?
Diameter is basically, so you know what is the diameter of one atom. So you can say what is the total diameter of that. Uh, so typically you can approximate it to be like a nearly spherical particle. Okay, so in that sense, this diameter is mentioned here. But this value of d, that can be different for different, like if you look at the bottom, so the value of d will be different uh, for different structures, for different atoms. So argon, gold, copper. So D value will be different. But basically, this is like you approximate it to like a spherical particle, nearly spherical, and then you can calculate that, the dimension.